Oh, welcome back everyone so far. We're waiting out our minute and then we'll get started. Appreciate you making it in today, Parker. You're representing the Zoom side now. And it's official. Welcome back, folks. We're now kicking off week number 12 of the 16-week semester. So we're 75% done with after this week is over. Congratulations on making it here. This is like the toughest part of the entire academic school year. If it were fall semester, people are usually more energetic than we usually are now, but back-to-back semesters has a way of kind of draining us. But we'll get through it. Our job today is finish off section 4.2, first derivative test, second derivative test for optimization. Then we make slight adjustments to those tests in 4.4 so that we're actually going for the absolute maximum and the absolute minimum. And this is going to be our big application section next on optimization. Quiz number 7 is probably going to be based off a problem off of this list. And quiz number 6 is another optimization problem, but this one just through the closed interval method. So that's our goal working through this week today. After we finish 4.4, we're going to move into section 4.6 on so-called antiderivatives. But really what that section is all about is turning it over from differentiation problems into next integration problems in chapter 5. We don't have a lot of time to get through a whole bunch of concepts in chapter 5, but we'll be ending on some integration techniques just to see what is the integral calculus all about and a couple applied problems as well. So that's our goal so far with the rest of the semester. If we take a preview of the upcoming weeks, we have ordinary week next week, exam week the week right after that when we scroll to this level. So that means whichever section we finish off at 100% completion will be the last section attached to exam 3. It also means this is a busy weekend as well. This is a weekend where, just like with exam 1, exam 2, I'll be putting down all the information to help prepare for exam 3, starting with the actual formula sheet attached to that third exam. So that's our goal so far. Any questions at the moment? Okay, further on in the announcements, scrolling down, closed week is a new policy for ISU. Actually, this was effective last semester, but I missed the memo on that one. What closed week means is we are discouraged from having anything like an exam or major project assigned or covering new content. This is going to be really just a complete review week for us. Then there's also a couple extra credit opportunities floating around. First one is really been on the table this whole time. At any point, if you get behind on WebAssign, the due dates there are really just for keeping at pace with the course. It's a benchmark you have to pass to be at pace. But any section that has gone late, you can request an extension at any time and complete that work for full credit. If you have any trouble with the extension system of WebAssign, don't hesitate to email me. I'm happy to put that in for you if that's been a little bit bothersome. Second extra credit opportunity is relative to the exams. If at any point you had, say, a really rough exam, this extra credit opportunity is more about if you came back on the final exam, learned those concepts well that you might have missed on any one of those exams there, then the final exam grade will replace your minimum grade among exams 1, 2, and 3. That's a pretty actual confusing statement there. So I feel like an example goes along with it. What I mean about this extra credit opportunity is, suppose for a totally made up student, exam scores are 91%, say really off day for exam 2, 67%, coming back strong on 89%. I think a lot of students would be pretty happy about that. But in the sake of total fairness, if this was an off day for you and you scored 95% on the final exam, I feel like you really should have made that up. You came back strong on those concepts. And the whole purpose to the exams is to determine your understanding. So if you had 95%, then your exam 2 grade gets replaced as the 95% on the final exam score. If For another student, the exam score was 65%, then that doesn't beat anything on the minimum score. That would mean no change. Your exam scores will be kept exactly as is. So that's how the extra credit opportunity runs. And one of the reasons I never curve exams 1, 2, and 3, I'm not sure if I mentioned that, but I never curve the exams, is because I want to see where the class falls at the very end after exam 3. I do curve the final exam. My objective with giving a final exam is it should never move the entire total average for the whole class by very much. If I assign a final exam that dropped the total average for the whole class by, say, 5%, I probably would curve the final exam to just make that up. My goal is to keep your grade right about where it is when I go to write one of these here. So when the extra credit opportunity hits, it's going to be the curved final exam grade really that gets applied to this method here. That's a lot of words to describe that 5 minutes into the announcements. But any last questions or comments, folks, about anything we've discussed so far? Okay, short of it is we're on a pretty relaxing week right here, just business as normal, but on the weekend, starting on Friday, working through the weekend, latest you'll start seeing information is going to be Sunday if I'm quite behind. Earliest might be as, say, Friday out in the afternoon if I'm a little more ahead. You'll see the information here so you can prepare studying for your exams. I'm a fan of parallelism, so you'll have pretty much the same exact stuff you saw in exam 2. Formula sheet, let's see here, sample exam 2 exercise versus 1, and then version 2, and then version 3, in the same kind of format for those. And if we need a review, if people have questions on Thursday before that exam, we'll do another one of these, an impromptu review day ahead of that exam 3. Well, we left off on section 4.2. Not exactly here, but this is a good part to come back to just to get a kind of a warm up before we finish off the next problem. We started section 4.2 on optimization by first taking a look at the first derivative test. But really, when you think about this, the major tool we used here was really the increasing decreasing test, which tells us if the function's derivative is positive, the function will be increasing. If it's negative, the function will be decreasing. And so we found it was an increasing, decreasing, and an increasing function in that order. First derivative test will tell us if we go from an increasing function to a decreasing, well, there's got to be a local maximum somewhere right around here. And that's what we said. Local maximum is the output when we plug in 1 and get 2 out. So 2 is that local maximum. And likewise, if we go from decreasing to increasing, we're looking at a local minimum. And that's what we found here, right across the critical number 2. So we get critical numbers, we feed them into a diagram like this in any kind of format that makes sense to you. I usually write a number line in this way, analyze the sign of the derivatives, and make our conclusions. So this is if we're thinking about local maximums, local minimums. We turn the concept over entirely to concavity, what feels like a whole unrelated concept. First, here's what concavity looks like. We'll say the curve is concave down if it lies below tangents, and then concave up if it lies above tangents. But to actually find those intervals of concavity exactly, we use the so-called concavity test. Really, though, when you look at this very carefully, the steps we take here feel identical to the very last problem when it was about increasing and decreasing. The only major difference is we go down to the second derivative, find the critical numbers, we found them, 0, -3, +3, go to a number line or any other way to analyze this information, because we're looking into the sign now of the second derivative, and similar concept, except we'll say, if the second derivative is negative, the curve is concave down, it is below its tangents. If it's positive, the curve is concave up, it's now above its tangents, and so on. So we found the intervals of concavity through the concavity test. What we have not yet found is the so-called inflection points on the graph. But I think I broke something when I did that. Let me see if I can fix this. Okay, those are just all attached to the definition, it looked like. So next, the inflection points. This is like the step where we were looking into local maximums, local minimums, except you have to be a little bit careful with inflection points. A point of inflection is let's write down just a quick statement here. Points on inflection on the graph, let's just go that far, means a point on y equals f of x, where concavity changes. So that's what we mean by an inflection point. Because we keep emphasizing a point on the graph, there's two coordinates. We have to feed in the x coordinate and the y coordinate for this kind of problem. Also notice we're talking about the original graph, y equals f of x. This is where it gets kind of confusing. We filled out the sign chart relative to the second derivative, and we did that for critical numbers that came from setting the second derivative equal to 0. There's also a first derivative, but we don't do anything with that one. We go all the way up to the top. The original function is what we have to use to find the points of inflection. So go back to this original function that we started with. Come down below. Hide the second derivative test for a moment. And now we're ready to get those points of concavity. So it's all about what happened on the critical numbers, and also where concavity also changes. Here we're concave down to concave up. So we'll get an inflection point at -3. Let's say the inflection points are here's the first one, grab -3 at the red dot, but it's a point on the graph of f. So we go now plug it into that function down below. Let's see what this comes out as. It's -3. F at -3, let's just make the calculator do the job for us. So that's going to be a -3 to power 4 out of 27. So we'd be taking the natural logarithm of 108. So f at -3, just natural log 108. So that was through this point right here. But this is a interesting problem. I chose this problem specifically because this is really confusing suddenly right here. Let me target that a little bit better. It's really confusing right here. There is no inflection point at 0. Because concavity is positive here, we lose concavity. The second derivative is exactly 0. But then we're concave up again. We never had concavity changing. No inflection point at 0. That's really kind of strange in a way. That's tricky enough to write down as a separate comment. Let's say here, no inflection at 0 f at 0, which is a point on the graph at 0, natural log 27. So we didn't have any inflection point. Concavity stayed the same across both. Then when we go to the next one, nothing too unusual here. We went from concave up to concave down. That is a change in concavity. So new inflection point, right at 3. So it's going to be 3, f at 3 equals 3. We're plugging 3 back into this function, but we get the same exact value, natural log 108. So those are the two inflection points that satisfy the question finally. You don't have to write down this comment whenever it happens. That's mostly for the sake of the notes, because it's so tempting to say 0, natural log 27 is also an inflection point. We did it, folks. That's the full process dealing with concavity. Again, it's just like finding local maximums and minimums, but we just go to one higher order derivative on the sign chart, second derivative. Any questions at all with the full process? Okay, this is the full analytical side of doing this whole thing. To really tie down these thoughts on what's happening with concavity, we should look at a graph. So let's tie this all together with a graph of that function. I already forgot what the function was. I shouldn't have deleted that. So it's going to be that function right there we're throwing in. F of x equals natural logarithm x power 4 plus 27. Weird looking graph already. What we're really interested in is not local minimums like down here, but what happened with concavity? So we have some claims that we made right over here about concavity. Let's check them out. Concave up from -3 to 0 and 0 to 3. So from -3 right around here, hang on, -3 is right around here, all the way to 0, we claimed it was concave up. No concavity here, this is where the second derivative is 0. And then concave up again from this range, 0 up to 3, so just shy right around here. Let's see if we can make sense of that. I put a tangent line here. The curve does in fact lie above that tangent line. Same with one right around here. So that does look in fact like it would be, yeah, concave up in this region. Right around -3, that's where there's a change somewhere out here. And +3, there's another change in concavity. We're claiming concave down on that range to the left of -3, and then again symmetrically to the right of +3. So let's see if we can make sense of that. Right around here, I'm pretty far away from -3, where we had an inflection point right at that region. We draw a tangent, say, way out here. Oh, let me try again. We draw a tangent, say, way out here. These are slightly harder to draw tangent lines, but this one would look about like that. Another one way over here would be a tangent line that looks about like this. And yeah, now the curve is below its tangent, concave down, like we said here. Right around here is a point of inflection. That's what we said right over here, around -3, 108. Inflection point, which means transitioning to concave up. And notice, still concave up right around here. No concavity in that spot, and then concave up again until we go to concave down. So second point of inflection, +3, natural log 108, somewhere in that location. So here's a last screenshot just to show what in the world did we do with all this analytical work. Next thing we'll be taking a look into is a second derivative test for local maximums, local minimums. But any questions at all, folks? Taking a look at concavity and seeing it down the graph. Okay, so next is the second derivative test. This is a really powerful test when it comes to optimization. And then the very next section, we'll practice it once in this section as well. But it is a weird test in full disclosure, because what it's telling us is, like we talked about last Thursday, feels backwards. It says if the second derivative is positive at a critical number c, making the first derivative 0, then positive goes to a local minimum. If the second derivative is negative at that critical number, negative goes to a maximum. That's so weird and harmful to the brain when directionalities seem like they're mismatching that we need a diagram just immediately on this problem. It's talking about local minimums, local maximums. So the best diagram to grab would be not that one. Let's go all the way up to this one. Actually, let's just take a full-on screenshot or annotation as well on it. Let's drop it right into the second derivative test. Let's see if we can make heads or tails of what all this information is trying to convey. So first, even if you're using second derivative test, you still need a critical number. And the critical number is a value that makes the first derivative go to 0. We'll see a value right here. That's a critical number. Horizontal tangent implies the derivative is 0. Another critical number here at 2, horizontal tangent line. So we do have, in fact, have two critical numbers. Now on this region, it's concave down. But that means for all numbers we pick in this region, concave down means f double prime, x less than 0 by the concavity test, the last problem we were running. Over here, we're concave up, and visually it definitely looks that way. The curve is above its tangents. Yet the concavity test, the very last problem we ran, says concave up means f double prime at x, where x is in this range, has to be positive. So I love the concavity test. Down for negative, concave up for positive does make sense to my brain. But look at what else we see here. Concave down did in fact lead to a local maximum right over here. Strange. So we have a local maximum. And this happens in a region where f double prime at C, well, it's concave down, so less than 0. So there's that mismatch. A maximum where the second derivative is negative, then likewise over here, we have a local minimum. And in this entire region, f double prime at any value, including a critical number like C, is going to be positive. So that's the second mismatch. It's not a real mismatch. It's a real process that's happening. It's just that when it comes to concavity, local minimums and local maxes, positive on the derivative means the minimum, and negative on the second derivative means you found a maximum. There's no getting around this. This is just the nature of concavity. Kind of weird, but I feel like a graph makes sense of it. Does that look like a convincing argument to you all so far? Awesome, I'm glad to hear that. Next thing we'll do is apply this test on an actual example. Notice though, one thing we kind of skipped across was this part. Just like in the very last problem, we were harping on there is no concavity here because right at this location, the second derivative is 0. It's not even an inflection point because concavity didn't change. It was down, or excuse me, concave up on both sides. So no concavity when the derivative, the second derivative is 0. We lose any information then. We don't know anything about concavity. So the second derivative test has one not so wonderful feature. This doesn't happen to the first derivative test. The first derivative test is fully conclusive on every single part of it. But if the second derivative is ever 0, we don't have concavity like we see here, and the test has failed. That's a strong word. What we mean by the test has failed is essentially the test is inconclusive. If it's inconclusive, that means there's 3 things that can happen now. We have a trichotomy. We could have case 1, f at C is a maximum. Or the other thing that could happen is that f of C is a minimum. Or the third possibility is that f of C is neither a min nor a maximum. So even if you find a critical number set to 0, it does not mean you have a local maximum or minimum whatsoever. Further work has to be done. And this is a stage at which second derivative test won't resolve it. We need the first derivative test to see which outcome occurs. So already, probably the second derivative test doesn't seem so nice, right? It looks complicated. You need a critical number. Then you feed it into the second derivative, and whatever the sign is, take a type of opposite conclusion. And it can become inconclusive where you need a first derivative test to fully resolve this. So the question you might have is, why do we want the second derivative test with all these struggles that we just put down? It's because it's fast. That's it. That's the whole reason. When the second derivative test works, it is an extremely rapid method to use. We're about to do some optimization in section 4.4. And so part of our work in this section is to decide when is the second derivative test the best option and when is the first derivative test the best option. It all just depends on how hard is the derivative and what might happen with this third case here on part C. When things go bad, becoming inconclusive, we just use first derivative test. But it's a fast enough test. We'll study it a little bit here on one more problem. So here's our last problem for the notes in 4.2. Here's a second derivative test, just restated for extra clarity. And we'll practice it on this function here, 3x⁵ minus 5x³ plus 4. Says use the second derivative test to find all local maximum values and all local minimum values. There will be a case where the test actually fails on this problem, but it's okay to just state that as a statement. We don't have to do anything further on this problem. If the instruction just said use second derivative test, we'll do our best we can with it. So in this process, here's step one. Very first thing we want to do to apply this test is take the first derivative. So we'll go h prime of x. It's a polynomial, so these go fast. This will be 15. x⁴ minus 15. x⁴2. So our derivative is down. We're now on that line. Our function is h, but still we're looking into this statement where we're dealing with the f function being differentiated. We found the f prime part at x, but now we want to set it equal to 0 and solve to get the critical number. That part we can call step 2. Before we jump into step 2, we could stay right here and just simplify our derivative a little bit further. H prime of x is this quantity, but we can factor out 15x², leaving behind x² minus 1. So this is our new format for the derivative, h prime. We can factor inside that group to get 15x², x minus 1, x plus 1, after factoring that difference of squares. So now this is the first derivative, h prime of x, down to this line. In step 2, we solve h prime of x equals 0. So now we're at this stage altogether, solving that derivative, really on all lines, but only highlighting the first one here on part A. Solving this set to 0 just means plug in the left-hand side by substitution, 15x², x minus 1, x plus 1 equals 0, which then implies x is going to be equal to, just go down the line. To get 0 equals 0 balanced, right where the red dot is, pick x as 0. Balance the equation here, we'd have to be picking x as 1. Over here, pick x equals -1. And this is the full full set of critical numbers. Just to be specific, let's say these are the critical numbers of h. So we're done with that part. Now we're looking into these parts right here. But before we get there, we should first do the second derivative. So that would be a step 3 on this process. So here's our first derivative. It's in 3 different algebraically equivalent forms. This form in its raw expanded form, a partial factorization, a full factorization. But if you're going to h double prime, this is the interesting part of the work. You don't want to differentiate where the red dot is. That form is best in a simplified form for equation solving, but for differentiation, the most simplified form is at the very top. So differentiate on this line, and the process is way easier. So multiplying 4 by 15 using the power rule, we'll get 60 x³. Differentiation here, we'll multiply 2 by 15 to get -30 x. So now that's our second derivative. We're now on this part. At the same time, we'll be making our conclusions on the right-hand side as we go to analyze the sign. Let's call this a step 4. But really at step 4, our job is done. We're just going to take the critical numbers, feed it back into the second derivative, and just see what is the outcome for the sign. Whatever the sign comes out as will inform us if we have a local minimum or a local maximum, or when the test fails, like it will in this problem at one specific number. So here's what the last bit was going to look like. Let's do h double prime. Let's also highlight these, the critical numbers themselves. H double prime, I'll just go down the line, starting at 0. Second derivative at 0 means we're plugging 0 into this line. That would just be 60 times 0 cubed minus 30 times 0, which is just 0. And that puts us in this situation. The test has failed in a really spectacular way. We don't have any information whatsoever about what happens around 0. Could be a local maximum, a local minimum, or nothing. All we know is that the derivative went to 0 when we plug in 0 inside this derivative and nothing else. Let's just make our conclusion. This means the test failed. Kind of a weird conclusion, right? We can't say anything further. If I'm using the second derivative test as the instructions inform, that's as far as I can take it on that first critical number. Kind of a sad conclusion, but we move on to the very next critical number, 1. So go h double prime that now, positive 1. We're plugging 1 into this line for x, so that's just 60 minus 30. Giving us a value of 30, which is greater than 0. And now the greater than 0 part tells us we're on part A. Second derivative at a critical number, positive, means we have a local minimum. So be really careful how we state this one. This implies the local minimum is going to be equal to h at the critical number 1. But notice we're talking about the original function h this time. We want the maximum or minimum on the graph of that function. So we're plugging 1 inside here to get 3 minus 5 plus 4, which is going to give us altogether a local minimum of 2. Keep in mind, the answer is the output, not the input 1. We want the actual height of the curve on the graph. So that's our local min right at height 2. Then we just redo this at the last critical number, negative 1. Grab negative 1, drop it into the second derivative right over here. Plugging a negative 1 in x cubed just gives us negative 1. So this will be negative 60. Negative 1 here will give us plus 30. Equals a negative 30. So now second derivative is negative at negative 1. We're on part B now. If it comes out as negative, it means we found a local maximum this time. So this implies the local max is the output by plugging in negative 1 into the original function h over here. That will give us negative 3 because negative 1 power 5 is negative 1. Negative 1 here from the cubed times 5, so plus 5, plus 4. So we have a local maximum value at height 6. And just for emphasis, that's the other answer, the output to the function. So we did it, folks. This is a strict use of second derivative test, even when the test fails at a critical number, just to show what it would look like. We all had to do one of those on the notes. Last thing we do with this, just to get some better understanding of what this test is trying to say, is just plot the function, and notably that would give us information what's going on right here on the critical number 0. But any last questions at all, folks, on just finalizing this method? Okay, other word of warning with this kind of problem is it's a lot about just being really, really organized. A lot of mathematics is like this. If you have to use the second derivative test, you have to be very mindful of which function is the original one, which function is the first derivative, which gives you the critical numbers, which function is the second derivative, where the test actually occurs right here. My best advice on that is just label everything, be descriptive. Actually call your derivative h prime of x. Actually call your second derivative h double prime of x. That way you're going to be able to tell apart between 3 different functions, and they all have to be used in specific ways through this analysis. But here's the fun part. Let's see just how close we got to getting our expectations met by plotting the function itself. H of x is 3x power 5 minus 5x cubed plus 4. So I definitely see 3 critical numbers there. Critical number occurs on a horizontal tangent, and it's horizontal up here, it's horizontal over here, and it's also horizontal there. But right at critical number 0, that's where the test has failed. At critical number -1, we said local maximum at height 6. That's exactly what the graph is providing. Critical number -1 gives a max at height 6 to the original function. Likewise, critical number +1 gave a local minimum at height 2. So that's that 2 there. But what happened right where it failed? There's nothing. It's decreasing. Sure, the derivative is flat here, but then it just continues to decrease again. So the first derivative test would have told us that. We would have had a negative derivative, 0 derivative, so a critical number, and then negative again. That would tell us no maximum, no minimum. It's just decreasing, pauses its decrease, and then continues again to decrease as well. These kind of problems are almost like a selling point when we go to section 4.4, the very next one, on why do we work so hard on these next problems? A lot of times when you see these next problems that we're about to solve, people feel like the job is done the moment we find a critical number to this. The reason we have to actually use the first derivative test on this problem is we're trying not to be deceived where a critical number gives this sort of outcome, no maximum, no minimum. We want something like that to really happen, an actual global maximum. Well, this is where the notes in section 4.2 end. Let's include this graph here just for the sake of emphasizing the weird thing that happened at that part. Well, any last questions at all, folks, on this section here before we try the next? Okay, let's give this a save. We'll get a short mental break. And now on to the next section. In the next section, like we mentioned before, we made a couple adjustments to our tests. Let's look at the first derivative test first, and then the second derivative test. The adjustments we're making are sensible ones because the goal is a little bit different this time. In 4.2, we're looking for local mins, local maximums. But this time, we want the absolute extreme values. In other words, we want the absolute maximum. We want the absolute minimum. So what changes this time is here, if the first derivative is positive, we're increasing for all x less than c. And if it's negative, then we're decreasing for all x less than bigger than c. That's the absolute maximum. It's really where we say for all x less than c, for all x bigger than c, on both of these, this is where we're getting the absolute maximum and the absolute minimums. It also says there's exactly one critical number as well. Everything less to that c, you're increasing. Everything right to that c, the critical number you're going to be decreasing, leads to the absolute maximum. And same idea for the absolute minimum. So it's the for all x here, the fact that there's one critical number, which is now targeting the absolute max, absolute min. We'll take a look into this test right after, but we're just looking into the second derivative test. This is our opportunity to practice it again. We'll do 2 problems with the second derivative test on this notes, another 2 problems with the first derivative test. And this one has also been adjusted ever so slightly for absolute maximums, absolute minimums. So the thing that's a change here is not that part. We still look for a critical number, so it sets the derivative to 0. It's this part. We're actually targeting absolute extreme values if we insist the second derivative is positive for all x in the domain of f. In other words, we'll be able to use the second derivative test to find an absolute minimum if we know that the curve is always concave up for every value in its domain. That's our big adjustment for the second derivative test. And likewise, if it is concave down for all x in its entire domain, so everywhere concave down, we have found an absolute maximum. So 2 small changes here, but with those changes, example 1 will lead to the, looks like, smallest possible value. We're going for an absolute minimum. Any questions at all, folks, about our slight change to that second derivative test here? Okay, example one is really short, and it's meant to be that way. This is like a warm-up problem in the notes. It says the sum of two positive numbers is 15. What is the smallest possible value of their sum of cubes? Honestly, you really don't need calculus for this one. The answer is take your numbers, 7.5, 7.5, cube them, that's the smallest possible value, and we're just done on that step. But we're going to do the full process on this problem anyways, even though it's a simpler one. The idea is we can understand what's going on in the simpler problem here by using the full method. It's a warm-up to when we have a problem like this one, where it really is built up this time, or a problem like this one, where there's a lot going on. This one's dual to example one. We're using second derivative test on this one. But there's a lot of analysis to do even before we get started. So think of example one, even though it's really simplistic, as a really good warm-up question. Let's run through this carefully, line by line, sentence by sentence. Starts up by saying sum of two positive numbers is 15. Let's now declare some variables. Let x, they're positive, so we want positive, x bigger than 0, y bigger than 0, satisfy x plus y. We're using x plus y because it's indicating the sum of them is 15. This equation is actually special. We'll call this equation a constraint. So now, after that, here's like where the question is posed. Well, I think I forgot the question mark on that. You know what, let's edit that. Might as well. So this was a legitimate question. What is the smallest possible value of their sum of cubes? It said there, right over here, so it's referring to the x and y that we just defined. It's talking about, let's see, a sum of cubes means raise y to power x and y to power 3. So this is telling us minimize x cubed plus y cubed. So that's our task. So we have a constraint on that minimization that the sum of those positive real numbers is 15. And we want to make their cubes added together small as possible. One thing we should do here is all of our optimization methods depend on a continuous and differentiable function. So let's declare a function immediately. F of x is going to be the sum of cubes. So we're minimizing f of x. This makes it feel like a question just like in section 4.2. We're using the second derivative test to minimize that. One big problem though. If I declare f of x as a function of the variable x, yet it outputs x cubed plus y cubed, we have a major notation problem. Y itself had better be a function of x, or else we can't do this calculus here. I can't differentiate with respect to x with the variable y inside there. So we go back to this constraint equation. We can turn y into a function of x just by solving for it. Let's write in y equals 15 minus x. Now it really is a function of x, so we can take this here, plug it into that location, and now we have an honest function for which we can really minimize. F of x is now equal to x cubed plus, in place of y, form the substitution, 15 minus x, power 3. So we are minimizing that function. Now calculus is back on the table. The process starts on the second derivative test. But any questions at all, folks, taking this whole line right here, getting the constraint and the function to minimize? Okay. When we go to now minimize this, we could use the first derivative test. It works just fine. But the instructions say show all steps using the second derivative test. And that's a wise choice. Second derivative test on this problem is nice because the derivative is so fast. So let's now say for step one, Mirroring the process on the last problem we did in section 4.2, just finished, start by just computing the derivative, f prime of x. Notice I didn't expand 15 minus x power 3. It's kind of an annoying expansion. I'm just going to differentiate it right in this format. The derivative of x cubed is 3x squared. This derivative is a chain rule problem. So let's run through this one. Every time we've done a chain rule problem, we've always done a little bit of extra analysis on it. But we're pretty far into chapter 4, so let me know how this feels. If I was going to differentiate this problem, and I felt like I've gotten a lot of practice on chain rule, I would do it this way. Take the derivative of the outer function, that's power 3 coming down through the power rule, and it would look like this, new power is 2. Then it would look to what's on the inside. The inner function is 15 minus x, so I would drop it right here. Then go times. We're multiplying by the derivative of 15 minus x. And that's usually what we wrote in here, derivative 15 minus x. But we know that derivative is going to be 0 on the 15. Derivative of negative x is negative 1. So if you wrote it this way, I would just assume you've practiced chain rule a lot. But how does that feel to folks? Does that make sense, writing it out in this way? Okay, just maybe one extra arrow for a clarification. From here to here, this part was chain rule. That's the first time we've done the derivative in that kind of format. Just go directly at it. The more practice you get at this, the more often it's done this way. So here's f prime of x. In step 1, we're done. We have the derivative, but now in step 2, we're targeting that part. We want to actually set this equal to 0 and solve. So maybe let's stay in step 1 a little bit. Solving the equation x is not looking nice based off this format. Let's do a little algebra and clean it up first. The algebra I would take is to move the negative sign in front over here. So let me reformat as 3x squared minus 3, 15 minus x, power 2. Next step to take is, let's actually expand 15 minus x squared. We would get 3x squared minus 3 times. FOIL method on 15 minus x times 15 minus x is first 15 times 15, 225. Then it'll be 15 times negative x twice, so negative 30x. Then it'll be x times x, so plus x squared. Next step to take is a distribution of negative 3. We have 3x squared minus 675. Let me double check that. 625 by 3. Yeah, 675 plus 90x minus 3x squared. And this is kind of a nice little bonus. Doesn't always happen algebraically, but we have a cancellation. Power 2 is canceled out, so the complexity in the equation solving has gone way down now. Now it's just 90x minus 675. So that's kind of nice. First derivative is just that after cleaning it up algebraically because of this mathematical miracle cancellation of power 2 term. And now let me take this as a screenshot so we're not scrolling up and down a whole bunch. Hate to give anyone motion sickness just from doing math. So now I shouldn't have done that. Let me blow it up again. We're still at the f prime step. Now we're moving to the f prime equals 0 step. And we can say for step 2, we're solving f prime of x set to 0. But that's really fast, right? Substitute where f prime of x is on step 2, the 90x, my 675 set to 0. A couple steps to solve this one gives us that 90x is 675. So x is 675 90ths. Let's approximate that if necessary. Let's see if it goes in evenly otherwise. So 675 90ths turns out to be 7.5 exactly. And this is the critical number of f. Notice we found exactly one critical number. That's key to this. We want to show for that one exact critical number, for going for an absolute minimum, that the second derivative is always going to be positive. And this is for all x. We don't even plug the critical number back inside of it. We just have to show and argue somehow our second derivative can never, ever be negative. Kind of a different last step on this. Well, almost the last step. Let's call this step 3. Step 4 is just going to be our conclusion. But in step 3, all it's asking us to do is calculate the second derivative. Show at x, it's positive. So here's the first derivative. Second derivative is based off differentiating that 90x minus 675. So f double prime at x is 90. Our job is done. This is why the second derivative test was picked. It's because it's fast. First derivative was fast, but if it was a hard one, we probably wouldn't like the second derivative. The second derivative is probably even harder, making the first derivative test the better approach. But now that we got that second derivative, let's see what happened. It's 90. That's a positive value for all x in domain of f. The domain of the function f, we never actually discussed, did we? But we did say the domain right here. X was meant to be a positive number, so it's just bigger than 0. That means domain of f is 0 to infinity. But it's a constant. It doesn't matter what x you plug inside there. It didn't matter what the domain was specifically. The second derivative is just 90, fully positive, not even depending on x whatsoever. It automatically qualifies for this portion down here in the second derivative test. This takes us to step 4. Step 4 is just a conclusion. We have an absolute minimum, and it's referring to f at the critical number. Here's our critical number, 7.5. We just plug it into our function f, and we get the minimum. So let's check our instructions one last time. It said, what is the smallest possible value, that's the output to the function f, of their sum of cubes? So we go to our f of x function. Here it is in a pretty nice format. Calculate f of 7.5, the critical number. At 7.5, we're getting 7.5 cubed plus, plugging 7.5 here is giving us 15 minus 7.5. That is exactly 7.5 again, raised to power 3. Now we're just dumping this into a calculator. I have 2 copies of 7.5 cubed, simplifying this algebraically by combining the like terms, gives us 843.75. And this is the absolute minimum sum of cubes. So that's the process, folks. Let's maybe go back to here, see if we can take a full view of the problem and solution. So when we specified the constraint equation, said we were minimizing a sum of cubes, this is what the whole process looked like. We take the derivative, find a critical number, but in the second derivative test, once we took the second derivative test, we had to observe always positive. And that's this outcome right here, which told us the absolute minimum is f at critical number c. So 7.5 plugs right back in. But we did it, folks. That's our first big optimization technique. We're really contextless math problem. What we want to do is redo this kind of thing for something that looks more meaningful. So we'll be doing stuff in biology, business, and then pharmacokinetics for the next examples. But any questions or comments before we try a next one? Okay, here's that next one coming in. Now, part of the goal in this section is to decide when is the best test. This one said second derivative test should be used. Made sense. The first derivative was fast. Second derivative was really, really fast after the first one. But now the next problem says, use the second derivative test, which is sometimes regarded as the harder one. It's not fast no matter what goes on. There's a lot of extra steps to show. But the reason it's the right test for this problem is first derivative on this is already hard. Second derivative is much harder. We might as well use the first derivative test in this kind of situation. So it's already a quotient rule. That's enough information to say, really, we ought to be using first derivative test on this thing. Well, before we even do that, let's read through the context. This one is a real applied problem. It says the rate in milligrams of carbons per cubic meter of land per hour at which photosynthesis takes place for some phytoplankton is modeled by this function. Who knows what operation is going on, but maybe I have no idea what this could be. Maybe we're doing some kind of chemical process or maybe some big large term experiment. And we were able to model photosynthesis for the growing phytoplankton in some patch of area. So that's where the unit's coming into play. Maybe not a patch of area. This looks like a volume of fluid. It's a cubic meter here. So we have a bunch of phytoplankton growing in maybe some kind of fish tank. We wonder what the photosynthesis will be, and this is modeling the rate of photosynthesis. It's a function depending on I. Here, I is light intensity. Here's a really weird unit. Light intensity can be measured as lumens. I think that's how a lot of people usually hear it, or in thousands of foot candles. Really weird unit, but it's a real one, I assure you. I Googled it before bringing this problem in. So we're wondering, if you're the head experimenter in charge of this, you've got a fish tank of phytoplankton, how intensely do you turn on the lights to maximize the rate of photosynthesis? They set it as, for what light intensity, I, is P, photosynthesis rate for the phytoplankton, maximized. Well, maybe one thing we should do before we even get started on this is say, I is the independent variable like an x variable. So think of I as being like x in just the prior problem. And also, I being light intensity means its minimal value is 0. This is total pitch black dark. In other words, we have a domain condition on I. Greater than or equal to 0. 0 means total darkness. Anything greater is now how bright we're shining these phytoplankton. Now you can imagine if I is 0, no photosynthesis whatsoever, your phytoplankton are slowly dying. So we turn up the lights. Photosynthesis starts to take place, and it gets higher the more you turn up the lights until we hit this point where it's optimal. Turning up the lights even further are now frying your photoplankton, and now photosynthesis is going way down. So P as a function, probably if we were to graph it, looks something like this. We want to know the exact right value for light intensity to maximize photosynthesis. So here's where the process will start. We're going to use first derivative test to find what light intensity is P at maximum. But look at the way they posed the question on this problem. The prior problem wanted the value that was the smallest sum of cubes. This one wants not the rate of photosynthesis, it just wants what light intensity, I value, that leads to a maximized rate of photosynthesis. So the I value is the answer. It's going to be a critical number, but we still have to show the critical number leads to the absolute maximum by showing all steps of the first derivative test. We're trying to avoid a graph that could look like this, for example, where there's a critical number there, but no maximum. That would mean just keep on turning the lights higher and higher for more and more photosynthesis. Seems unreasonable. Eventually, these creatures are going to just get fried at higher photosynthesis, but we actually have to show that. Essentially, what we're showing is the model itself is the correct model, that it's really behaving the way we would think it should, based off the biological background. So first thing to do on the first derivative test is take that first derivative right there. We've practiced this a little bit in chapter 3, but these are always pretty tricky. So let me know how this feels as we go. It's going to be a quotient rule. And because this is an applied problem with non-standard variables, I'll write it this way. Derivative of the photosynthesis with respect to the independent variable I. I wrote that weird. dp di is the way to write this in Leibniz notation, or you could just call this p prime if you prefer. No harm done going that route. Next issue is that it's a bona fide quotient rule, so let's be careful with this one. The derivative is hard enough already. I'll take 100i prime multiplied by I squared plus I plus 4, subtract 100i, this time just copied, but multiplied against I squared plus I plus 4, differentiated. So we differentiate the numerator, multiply by the denominator copied, subtract, copy the numerator, multiply by derivative of the denominator. That is our quotient rule process. We just need to divide by denominator squared. I squared plus I plus 4 squared. So there it is. We need to finalize two more derivatives, this one and this one. But let's do the strategy that we used way back in chapter 3 when we were looking into harder problems like this one. Let's let this one be our analogy to show that process. So by analogy, let's take y equals, I is the independent variable exactly like x. So we could rewrite this as, if we wanted to, x squared plus x plus 4. If we were differentiating this function, we would just write y prime equals 2x plus 1. That'd be the derivative of that polynomial function. Any questions with that derivative down there? Okay, so to make this analogy firm, we'll now say, take this part, put in the thing that we're actually interested in. Let's say now let p, well, let's not call it p, that refers to the total function. Let's just call it y again, generically. Let y equal I squared plus I plus 4. Then y prime will be, by analogy, the derivative of x squared is 2x. Derivative of I squared should be 2i. Over here, derivative of x was 1. So over here, derivative of I turns into a 1 as well. And the derivative of the constant is still 0 as always. So this is what we would put in for this part right here, just a 2i plus 1. Likewise, on this part, derivative of 100i, that's just 100, much like the derivative of 100x. So on our next line, we would say dp di is going to be equal to 100 I squared plus I plus 4 minus 100i times, on this harder part, this one is 2i plus 1. Yellow color coding just to show how that matched up from this step here. Well, now the denominator is that I squared plus I plus 4 squared. Now our goal is simplify this function as much as feasibly possible. But now you can see why the first derivative test was the right choice on this one. Second derivative test just means you have to differentiate this twice. It's not fun the first time, it's much worse the second time. But any questions at all getting to that step? Okay, let's hide the second or first derivative test just for the moment, because now our job is clean this up as much as possible. You have to do an equation solve on it, so this is a bad format for us. Now let's maybe do it over here on the margin, so we're not copying down a whole fraction step by step. So I'm focusing just on the numerator. 100i squared plus I plus 4 minus 100i, 2i plus 1 becomes, first thing to do is distribute that 100 in. 100i squared plus 100i plus 400, and I didn't quite leave enough space. Let's distribute this negative 100i into 2i plus 1. Here to here is going to be minus 200. I by I is I squared. And then here to here, a little bit easier, is just 1 minus 100i. So that's distributing everything through in the numerator. It does give us one nice cancellation here and here. I'd also like term to combine. We have 100i squared minus 200i squared. So I'll write this in as 400 minus 100 I squared. And every step we took here means we didn't have to write the fraction bar divide by this. We'll just plug that back in when simplified. But that factors now. It has a greatest common factor of 100, leaving behind 4 minus I squared. Then difference of square formulas for factorization comes up again. This is 100, 2 plus I, 2 minus I. So that last bit right there plugs back into our numerator. So let's call this, just for extra emphasis, dp di carried all the way down. Last line, dp di, first derivative, becomes not so bad in the numerator, just plug in 100, 2 plus I, 2 minus I up above. So to complete the arrow diagram, this just goes back up in there. Don't forget, it does have a denominator, I squared plus I plus 4 squared. So we've got it, folks. That's our first derivative, and it's full simplified glory. Next thing we do is, let's see. Suppose that C is a critical number of a differentiable function. Well, what that would mean is f prime at C equals 0, and that's telling us what our next step is. The moment we have a derivative, we set it to 0 and solve, whether it's the first derivative test or the second derivative test. So now dp di equals 0 implies we have some immediate solutions. Only way this is 0 is if the numerator came out as a 0. That could happen at -2 for this part. But recall I's light intensity. It had domain, which said non-negative values. 0 was the minimum. So we actually have to throw this away. This is out of domain. Domain is greater than or equal to 0. But let's do that in our next step. On this part, if I is +2, that's our next critical number. And that one is in domain. So we'll say, with that crossed out, and a note, out of domain. That's good for us because we did make a comment that for this to work correctly, there's got to be exactly one critical number. There it is. I equals 2 is the critical number of our function P, the photosynthesis rate. So now that we have the critical number, here's the sad part of this problem. No guarantee whatsoever the critical number leads to a minimum nor a maximum. It could be one of 3 possibilities. It might be a maximum, it might be a minimum, or it might be one of these. Back in section 4.1, we found a critical number on this function right here. We differentiate it much like our photosynthesis function. We set it to 0 and we solved, and there's a critical number, x equals 0. But just finding a critical number does not guarantee there's a maximum nor a minimum. In this problem, the critical number went like this, increasing at rest on the critical number, then increasing again once we go beyond. We're trying to avoid that picture. But to prove mathematically that it looks actually like this picture, a real maximum. So that's where the first derivative test actually starts to kick off. We need to take our critical number, I is 2, draw in a number line. The number line is going to look a little bit different this time. I want to put in the independent variable as a reminder, I, and let's say what it is. Light intensity. It does go off to the right forever towards positive infinity, but it's in fact capped off on our domain right at 0. This is where the domain starts. Total darkness. However, the derivative, the rate at which photosynthesis is changing, 0 right at 2, the critical number. So we drop that into that location, and we're trying to maximize photosynthesis. That's part A. That means to the left of the critical number, the derivative should be positive. Photosynthesis rate is increasing. And then I said to the right. That's to the left of the critical number. Sorry for misspeaking on that one. That's saying X less C. If we're over here to the right of the critical number, the rate of photosynthesis should be decreasing, meaning light's too strong. We're cooking the phytoplankton. That's what it's saying right here, negative first derivative. But to really see if that happens, we have to test this out. So we're looking into this interval and into this interval. Let's call this P prime because I had a space. P prime is referring to dPdi. A good critical number to pick in this range. Could you put 0 in there? I don't see why you couldn't put 0 into that one. It is in domain. Let's use that as our test number to start. Take 0, evaluate dP di. At light intensity I is 0. So this is the derivative. It's over here as well, but we're just evaluating at I is 0, and that would give us across the numerator 100, 2, negative 2, and the denominator is just 4 squared, so 16. And that's a negative quantity due to that part right there, the negative 2. So if that's a negative quantity, hang on, messed up that algebra pretty bad, didn't I? That's positive. If I'm putting 0 in there, that's going to be a positive 2 for 0, positive 2 again when I put in a 0. Let me fix this logic right here. Positive 2 on that end, so now bigger than 0. That makes sense because if we get bigger than 0, this means photosynthesis P is increasing on this range. Matching intuition, right? No photosynthesis at total darkness, but the stronger the light, the more photosynthesis increases up until a point. That might be the point. We have to check this out by another test number. I would say maybe 3 is the next easiest value to throw in. So dPdi, I set to 3. Back up here, numerator becomes 100, 5. And that's where we get something interesting. 2 minus 3 is a negative 1. Denominator is just some positive quantity due to the power 2 everywhere. That'd be 9 plus 3 is 12 plus 4 is 16. So it's just a 16 squared. Critically, all we care about is the sign. So I'm not as worried about the numbers, just what makes it negative or positive. But over here, we got negative for P prime, which means photosynthesis is decreasing. So at 2,000 foot candles, that's the optimal value, beyond which you're just harming the phytoplankton. Photosynthesis is going down. That means our work is done. We found one critical number 2. It says to the left of the critical number, we have a positive first derivative. To the right of the critical number, we have a negative first derivative. So there's an absolute maximum. Or you could view it this way, increasing till we hit 2, now decreasing. This is the shape of the P for photosynthesis curve if we were to plot it across that domain. So we have a conclusion. Let's say triangle is just a fancy way to say therefore, or in conclusion, all this work shows P is maximized at I equals 2,000 foot candles by the first derivative test. Our work is now done. All we were wondering on this is, at what value do you turn the lights on for optimal photosynthesis? In other words, for what light intensity is P a maximum? Weird question because it never asked for the maximum P. We just wanted the critical number right here. And we proved the critical number did in fact lead to that maximum. Sorry for going right up to the minute on that one. I think I just totally forgot to even look at the clock. It's kind of a weird problem, but any last questions at all, folks, on getting to the end of this one? Okay, well, have a great afternoon, folks. When we come back next time, we'll finish off these notes and potentially start with 4.6 notes as well. But have a great afternoon. Enjoy the warmer weather finally.